So, good morning class. Today we will discuss further about chemical bonding. In the last segments we discussed some basic concepts related to system and surrounding. We saw about state variables, path variables, that were state functions or path functions, and after that we discussed about work. Now we will continue further with our argument with work and with this discuss about heat. So, next would be, so in the last turn we saw that work is nothing but the product of force multiplied the small displacement. This was the work, and further we saw that if work done is on the system, then it is always taken to be positive, and if work is done by the system on the surrounding, then the work is taken to be negative. So, these were the conventions of work that we saw in the last segment. Now, we will further discuss about work. So, this work, when we are discussing about work, the magnitude of work depends on two factors, and the two factors are intensity factor multiplied by capacity factor. Intensity factor multiplied by capacity factor. For example, this intensity factor is always a constant term. Its value will always remain constant. But this capacity factor is a variable term. Its value will change according to the temperature or physical conditions near the system. Like if we take the example of work done due to gravity, that we can write W is equal to mgh, where m is the mass of the body, g is the acceleration due to gravity, and h is the height of the body above the surface or above the platform. So, in this case, this mass will remain constant, gravity will remain constant, but h value will increase as the distance will increase from the surface or from the platform. This means that in this case, mg is our intensity factor and h is our capacity factor. So, the net work done which is obtained in case of gravity, this is the summation of intensity factor multiplied by capacity factor, which is equal to summation of mg multiplied by h, and the work obtained is equal to mgh. This is the work done obtained during gravity or the work done against gravity. Again, if we take one more example, like the work done obtained during the expansion of a gas when the pressure is released. So, this work done is equal to minus P delta V. In this case, P is the constant term, so it is called intensity factor. P is our pressure is constant, it is our intensity factor, and delta V, which represents change in volume, it is our capacity factor. It represents the change in volume, and more will be the change in volume, more will be the work done. So, again in this case, work done is a product of intensity factor and capacity factor. It is a product of both the factors, and it is called product of intensity factor and capacity factor. And in this case, intensity factor is P, pressure, and capacity factor, which is variable, is delta V. And since work is done by the system, it is represented by a negative sign. So, the net work done obtained is equal to minus P delta V. So, this is all about work. We discussed further about work. The work done by a system is always governed by two factors. First one is intensity factor and the next one is capacity factor. Intensity factor is always a constant term, its value will not change according to the physical conditions or time, but capacity factor is a variable term and it is directly dependent on the magnitude of work. More will be the value of capacity factor, more will be the work done by that system or by that particle. Let us take first example. Now, when we are doing work against gravity in lifting a body from the height to a certain height from the surface, so the work done is obtained is equal to mgh. Now, in this case, mg is our constant term, which is our intensity factor, and height is the variable term, and this is our capacity factor. So, in this case, work done is again equal to the product of intensity factor and capacity factor. So, in this case, intensity factor is mg, that is mass and acceleration due to gravity g, and c of capacity factor is h, height. So, the net work done obtained in this case is equal to mgh. And when we are discussing about the work done by a gas while expansion, when the pressure is released, so in that case also work done is equal to minus P delta V. It is because minus sign represents because work is done by the system, and as per convention, whenever work is done by the system, it is always represented by minus sign, negative work done. Now, work done is equal to minus P delta V. So, in this case, P is our intensity factor, because P is a constant term, pressure will remain constant, but delta V is change in volume and it is our capacity factor. Its value will change according to the time and physical conditions. So, again here work done is a product of intensity factor and capacity factor. So, in this case, pressure is our intensity factor and change in volume is our capacity factor. So, the next work done obtained in this case is equal to work done is equal to minus P delta V. So, this is the work done obtained when work is done against gravity, and this is the work which is obtained when a system is allowed to expand when the pressure is released. So, always work is governed by two factors, intensity factor and capacity factor. Now we will further discuss about the work done, that term, that work done is equal to minus P delta V. We have to derive it, this expression we have to derive, that is the work done in case of a piston or in case of a gas when it is allowed to expand. So, we have to see derivation of work done or derivation of the formula, that is W is equal to minus P delta V. We have to derive this formula. So, since we have to derive work done is equal to minus P delta V, let us consider some arrangements. So, let this be a vessel which is filled by a certain gas. Certain gas molecules are present in this, and this is connected by a piston. This is connected by a piston. Now, let the pressure be released, and when pressure will be released, this piston will be lifted upward. Let the change or let the expansion be equal to small a length element, that is dl. Now, we know that pressure is equal to force upon area. Now, if we have to calculate force, it will be equal to pressure multiplied by area. This is our equation first, and we know that work done is equal to force multiply displacement. So, if there is a small displacement dl, the work done will also be small, that is we are taking it to be dw, small work done, and the force, the value of force is equal to P multiplied by A, where P is the pressure of the gas and A is the area of cross section of the vessel. Now, if net work done or small work done is equal to P multiplied by A, and with displacement we have seen it is equal to, this is our force and displacement is equal to dl. So, this is our force term and this is our displacement term. Let this equation be equal to 2. Now, we will modify this second equation and we can write in this expression dw is equal to, now in place of this area multiplied by dl, area multiplied by length element is always equal to volume, and since there is a small change, the change in volume will be also be small. So, we can write it will be equal to P multiplied by A, and it will give change in volume dV, because area and length is all with the product of area element and length element is always equal to volume element, and since where here length element is small, that is dl, the change in volume will also be small. So, this is our next expression, third, where dV is the change in volume, small change in volume. It is the small change in volume. Now, let the expansion be taking place from V1 to V2, where V1 is the lower volume and V2 is the higher volume. So, integrating equation third, क्या मिलेगा हमें, what we will get while integrating equation third? So, integration of dw is equal to integration of P dot dv, it will be integration of this term, and since pressure is a constant term, we can write integration of dw is equal to, P will be out of the constant integration term, and it will be equal to integration of dv. That is, we can write this will be equal to complete work done W, and this will be equal to P higher volume minus lower volume. So, this expression P2 minus V2 minus V1 can be equal to W is equal to P delta V, and since work is done by the system, because this piston is expanding and this is our, this piston is expanding, it is moving upward and this is our system. So, the work is done by the system, and the work done by the system is always taken to be negative. So, here the net work done obtained will be equal to minus P delta V. And here we can write, let the expansion taking place between V1 and V2. So, this is the final expression which we got in case of this work done, that is during the expansion of the gas, and it is equal to W is equal to minus P delta V. So, this is the complete derivation of the equation, that is W is equal to minus P delta V. Now, so this was derivation of work done, that is W is equal to minus P delta V. First of all, we took a beaker containing some gaseous molecules, and this is our piston, and this is our gaseous molecules. So, the pressure, when pressure will be released, in that case, when pressure will be released, in that case, there will be a change in volume, and let during the change in volume, the small change in volume let be dl. dl is the small length element by which expansion is taking place. So, we know that pressure is equal to force upon area. So, from this expression, force can be calculated to be pressure multiplied by area. Further, we know that work is equal to force multiply displacement. So, because there is a small displacement in piston, so the again work done will also be small. Let the small work done be equal to dW, and this dW will be equal to, force was equal to PA, P dot A, and displacement is small and it is equal to dl. So, this expression will be equal to dW is equal to PA multiplied by dl. Now, this product of area element and dl element can be written to be equal to volume, and since the length element is small, so the change in volume will also be small. Modifying equation second, we get dW is equal to P by dV, where dV is a small change in volume. Now, let the expansion be taking place between V1 and V2. These are the limits, because we have to integrate. So, V1 is the lower volume and V2 is the higher volume. So, when we will integrate equation third, we will get dW is equal to integration of P dot dV. So, this, because pressure is a constant term, it can be taken out of the integration equation function. So, this will be equal to dW is equal to P integration of dV, or this integration will take place from V1 to V2. These are the limits. So, or this work done will be, this integration of dW will give us the entire work done, or work done is equal to P V2 minus V1, or V2 minus V1 can be written equal to P d delta V, change in volume, and the final expression which we are getting, W is equal to minus P delta V, because in this case work is done by the system, and whenever work is done by the system, according to convention, work done is always taken to be negative. So, in this case, the net work done is always taken to be negative, and the final expression which is obtained during expansion of gas is equal to W is equal to minus P delta V. So, thank you class.